Yes, well, thank you very much. And obviously the story of Gromov-Witten invariants is vast, and I'm just going to be talking about a very small part of it, but a very interesting part. And I'm going to be emphasizing the point of view that I touched on last time, the relationship between, on the one hand, the theory of functions in differential polynomials, that's sort of the integrable system side of the story, and on the other hand, the large phase space picture, which is the sort of representation theory or Virasoro side of the picture, and the interaction between those two sides and the comparison of the same formulas written in those two languages is a large part of what I'm going to focus on. So much of this I want to emphasize was developed by Dubrovin. There were important contributions also by Giventhal, and I've listed just a fraction, but the most important fraction of some of the other people who've contributed importantly to this. I realize as I look at it that I've left out already one or two very important names. So perhaps there'll be a final version of this slide issued later, which will have an even more complete list of the most important names. Okay, and a lot of the formulas that I gave in my first talk and that I'll give in today's talk can be found in my review article, the Virasoro Conjecture for Gromov-Witten invariants, which you can find on the archive or also in the library. And today, there are two other review articles that I'll use. Well, one of them is my review article on the jet space of Frobenius manifolds. I'll use a lot of formulas from that paper today. Also, there's a very beautiful, more recent paper by Buryak, Postuma, and Shadrin, which really presents a lot of the story of the Virasoro conjecture and of the work of Dubrovin and Zhang in the language that I'd like to talk about next time. So the list of references in that article is particularly complete. And so if you look in that article and the places it refers to, then you will have a good understanding of the subject. Okay, so I'm going to focus on a projective algebraic manifold over the complex numbers of dimension R. So actually, a lot of the results do extend to compact Kähler manifolds, which, as you know, have many features in common with projective algebraic manifolds. It's just that they don't have an ample line bundle. Or if they do, then they're projective, sorry. And even some of the results in genus 0 Gromov-Witten invariants will extend to general compact symplectic manifolds. But going beyond general compact symplectic manifolds, it's quite hard to understand what might be true. Okay, so we can look at the closed algebraic curves in our algebraic manifold X, and we can look at their degrees. Those are elements of the second homology group with integral coefficients, and we can look at the monoid of such homology classes. And then what you see is this basic property that the number of decompositions of any element of this monoid into a sum of two elements is finite. And what that means is that rational functions on this monoid forms a commutative ring called the Novikov ring. And I hope you'll have met this ring in some form in one of the other talks. You can see that an element of the Novikov ring can be denoted by a sum. It's actually an arbitrary, I'm going to allow an infinite number of the coefficients to be non-zero, not just a finite number, so it's an infinite sum. And A sub beta will be rational numbers, and Q to the beta is just a symbol for the value of our function at the degree beta. Beta is an element of the monoid. Okay. And it's interesting to note that the ring lambda is actually graded. We can grade it by the anti-canonical divisor of the variety X. So the first Chern class of our manifold, and we intersect that with beta to get an integer, which is the degree. Okay? Well, I'm not going to emphasize this grading terribly much in this talk. Now, the basic object of study of the subject is the generalization of the Deligne-Mumford moduli space of stable curves, which was introduced by Kontsevich and carefully constructed by Berend and Manin. They used the same methods that Deligne and Mumford used to construct their moduli spaces, namely geometric invariant theory and the theory of the pluricanonical divisor. So the moduli space MGN beta, it's a moduli space of maps from a projective curve to X with degree beta. The curve has arithmetic genus G, and in addition, we'll have n smooth, distinct points labeled on the curve. And so that's our moduli space. It's actually a Deligne-Mumford stack. It is proper, but it's only very rarely smooth. For example, it'll be smooth when the genus is 0 and X is a generalized flag variety, a projective homogeneous space, like a projective space or a Grassmannian. Now, let's talk more about the nature of this moduli stack. A stable map, the domain of the stable map will be C, and the marked points will be Z1 up to Zn, and the map itself will be denoted F. Now, the curve C is restricted in the similar way to in the construction of the Deligne-Mumford moduli stack. C only has double point singularities. It has no worse singularities than that. Otherwise, it's smooth. And in addition, we assume that the map F has no continuous automorphisms. So what that comes down to saying is that on any rational component of C on which F is constant, there's a condition that it have at least 3 special points, either double points or marked points. So that's a complicated construction, but anyway, this moduli stack has been constructed and it's a basic object of the theory. Now, although in general this moduli stack is not smooth, it carries a replacement for a fundamental class, which it would have if it was smooth, namely the virtual fundamental class, which was conjectured to exist by Kontsevich and constructed by Berend and Fantecchi. So it's an algebraic cycle. It's in the Chow group of this stack. It's well defined up to rational equivalence, and it has the following dimension. You can read the formula. The formula involves the dimension of X. It involves the Chern class of X. It involves the genus, the number of marked points, and the degree. And it involves this in this way. I just want to look at this formula for a moment and remark that there are 2 special cases of this formula which are worth noting. One special case is if the dimension of X is 3. Somehow, the number 3 has a very special role in this whole subject. And you see that if the dimension is 3, then the moduli, the virtual fundamental class, has dimension independent of the genus. And I want to remark that that number 3 can be also viewed as the dimension of SL2, the Lie algebra, and somehow that Lie algebra SL2 is related to gravitation in 2 dimensions, topological gravitation in 2 dimensions. And so for physicists, the presence of this number 3 ultimately comes down to the fact that we're doing something called topological gravity in physics. Well, mathematicians have a different way of looking at it. They understand it through the Riemann-Roch theorem, which is where this formula comes from. Okay, so the other special case, which is worth noting, is if X is a Calabi-Yau variety. In other words, if the first term class is 0. And in that case, the second term vanishes, in which case the dimension of the virtual fundamental class is independent of the degree. And you see that in particular, for Calabi-Yau threefolds, the formula simplifies tremendously. The virtual fundamental class has dimension n, which is why the case of Calabi-Yau threefolds plays such a special role in the theory of Gromov-Witten invariants and is somehow much deeper than the other parts of the subject. Okay, so somehow the virtual fundamental class measures the fact that there can be obstructions to deformation of stable maps. And so we get a certain sheaf of obstructions, and somehow the difference between the tangent cone of the stack and the virtual fundamental class is something like the Euler class of this obstruction sheaf. That's in fact, roughly speaking, how Berendt and Fontecchi are able to construct the virtual fundamental class. Now let me focus for a second on the case of degree 0. I'll come back to that on the last slide of today's lecture and say a bit more about that tomorrow. In the special case that the degree is 0, then, let me go back a slide, then a stable map of degree 0 is just a constant map. So the stable map is just the curve C, which has to be stable, the marked points, and a point in X, which is the image of F. So that means that the moduli stack is just the product of MGN bar and X. And then we get an explicit formula for the virtual fundamental cycle of Kontsevich. It's the Euler class of a bundle that I'll come back to in a moment, capped with the fundamental class of this moduli space. The moduli space is a smooth Deligne-Mumford stack. It has a nice fundamental class, which is a rational class in the Chow group. And the cohomology class that we're capping it with, this top Euler class, what we're doing is taking a rank G vector bundle over MGN bar, which is the Hodge bundle. Its fiber at a point is just the abelian differentials, the algebraic one forms on the curve C at that point in the moduli stack. Well, actually, sorry, that's correct over the smooth locus, and at the boundary we have to modify we take the dualizing sheaf, which is modified by poles at the singular points. Anyway, we form a rank G vector bundle over the moduli stack, and we take its top, we tensor it with the tangent bundle of X, take the top Euler class, and cap it with this fundamental class, and you can do the arithmetic. You'll see that this does have the dimension which we've given on the top line, namely 1 minus G times R minus 3 plus N. Okay, I'll come back to this formula later. Okay, so now I have to define the Gromov-Witten invariants. So these are a generalization of those rational numbers that I introduced in the last lecture. Now what I'm going to do is choose a homogeneous basis of the Betti cohomology, or rather the Dolbeau cohomology of our projective manifold. So I'm going to take an indexing set, capital I, and elements of the indexing set I'll denote by small letters A, B, C. And the cohomology classes, gamma A, they will have Dolbeau numbers P, A, Q, A. Okay? And we're going to have a special role will be played by the identity element of the cohomology ring, which will denote gamma 0. So 0 is a distinguished element of our indexing set I. Then we have a non-degenerate inner product, on our cohomology space, and the coefficients of this inner product, the Poincare form, are denoted by eta AB, and then it's non-degenerate, so we can invert it and get eta upper AB. Okay, we'll be using both of these matrices throughout the talk. Now, the other ingredient we need for defining the Gromov-Witten invariants are these line bundles on the moduli stack of stable maps. And these are defined in a very similar way to the way that they were defined just on the Deligne-Mumford moduli spaces. We have the domain of our stable map, C, and we have n smooth points on this domain C. And so we can take the tangent lines at those points. So take the tangent line at the ith marked point, and in that way we get a line bundle over the whole stack. We can take its characteristics, its Chern class, and we get an element of the Chow group, in fact, of the stack, whose image in the cohomology is an element of H2, and we'll denote this by psi I. This all sounds perhaps a bit frightening if you've never really studied the cohomology groups of Deligne-Mumford stacks, but in fact it's a lot more straightforward. It's really just a question of getting notation straight. Okay, and the last ingredient we have is the evaluation map, which evaluates our stable map at the n marked points. So this goes from our stack to x to the n. So the basic idea of Gromov-Witten invariance, which I think really goes back to the invention of topological field theory, which I'm going to assign to Donaldson. So Donaldson was interested not in pseudo-holomorphic curves or algebraic maps from curves. He was interested in instantons, and he introduced the Donaldson invariance, but to a degree, the construction is quite parallel to what we're doing here. And the basic idea, I think, goes back to Donaldson's very important paper on the Donaldson polynomials. Okay, so now we have the definition of the Gromov-Witten invariance. So we'll choose natural numbers k1 up to kn, and cohomology classes gamma a1 up to gamma an, and then the Gromov-Witten invariant is the pullback of the cohomology class gamma a1 tensored with up to gamma an, which is a cohomology class on x to the n, pulled back to the moduli stack. We cup it with psi1 to the k1 up to psi n to the kn, and intersect that with the virtual fundamental cycle. And if the dimensions all line up, so if the sum of k1 up to kn plus pa1 up to pan is equal to the dimension of the virtual fundamental cycle, then this is this may be non-zero. So notice, just incidentally, it's a very confusing part of the subject that the same dimension formula holds where we replace P by Q. And personally, I find that a rather confusing aspect of the subject. We could be using Q everywhere that you'll see P in the formulas for degree. And it doesn't really matter which one we take, but the subject is equivalent under a conjugation. The reason they're called Gromov-Witten invariants is if you deform the complex structure of X, the invariants stay the same. In fact, the theory of Gromov-Witten invariants has been extended to general compact symplectic manifolds. So what we learn is that actually these Gromov-Witten invariants of projective manifolds are also the Gromov-Witten invariants of any compact symplectic manifold, which is the underlying symplectic manifold of a Kähler structure on a projective complex manifold. Okay, so moving on, I'm going to form a generating function for the Gromov-Witten invariants. We sum over the degree. And so we get these Gromov-Witten invariants now, which are elements of the Novikov ring lambda. That's a very convenient way to think of them, that the ring lambda is an extension of Q, which captures all of the fine information about higher degree Gromov-Witten invariants. Okay, and now again, as we did in the case of pure topological gravity, we're going to form generating functions for all of these Gromov-Witten invariants in genus G by introducing a formal space with coordinates corresponding to, there's one coordinate for each natural number k, and for each index in our basis of the cohomology. So this is some infinite dimensional formal algebraic variety, and we get this function in the power series ring, which is given by this explicit formula. And we could also form the generating function for all the genera at once by introducing an extra parameter, which I'll denote by Planck's constant, just like in the pure case. Okay? Now, remember that when we studied the KdV hierarchy, we actually focused on the second derivatives of f. And we can do the same thing here. You can take, and now what we do is we take k1 and k2 equal to 0, and a1 and a2 equal to respectively 0, the identity element, and another element. And in that way, we get basic functions on the large phase space power series, and you can show, as I'll explain that a little bit later, you can show that these functions actually have a very similar behavior to in the pure case. They're given by the T0A coordinates up to higher order terms. But actually, unlike in the pure gravity case, we prefer to just look at the genus zero limit of these coordinates. So the same limiting formula holds, but instead of using f here in the definition of the coordinates, we're going to use f0. This substitution is the key idea in the study of Frobenius manifolds. So actually, I'm going to not explicitly say when we're studying Frobenius manifolds today. Instead, I'm just going to say that the study of these coordinates is implicitly the study of Frobenius manifolds. Effectively, the spec of the ring generated by the UA is the Frobenius manifold. Okay? So the proof of these limiting formulas just comes about because in the very special case of the moduli space in degree 0, M03 bar x, that's just x. That's just the modulo space x. That's because the moduli space M03 bar is just a point. And so what that means is that the very special degree 0 Gromov-Witten invariant is just the intersection form. And so in that way, we see that the cut product is built into the definition of Gromov-Witten invariants. And in fact, for higher degree, the Gromov-Witten invariants with G equals 0 and N equals 3 are called the quantum product. But I'm not going to be emphasizing that in that perspective in today's lecture. Okay, so now I'm going to introduce, just as we had in the last lecture, a ring of differential polynomials. Actually, they're polynomials in the derivatives of u and power series in the coordinates u. Here, wherever I write u, I mean u superscript a, the whole vector of coordinates corresponding to the cohomology group of x. And the kth derivatives here are with respect to the very special direction in the large phase space, which corresponds to the identity element with k equals 0. And then in that way, we can define a derivation of this ring, which just takes derivatives with respect to this formal parameter. And we're going to be very interesting in a filtration, an increasing filtration of this ring in which we only take derivatives up to the kth derivative of u. Okay, we'll see that come up a lot in the study of the Gromov-Witten invariants and the Virasoro conjecture. Okay? Now, to make further progress, we need to introduce the topological recursion relations. So this requires a generalization, forget what I just said. Okay, so we're going to observe that as long as the moduli space M bar Gn is not empty, we can construct morphisms from the Deligne-Mumford stack of stable maps to the Deligne-Mumford stack of stable curves by forgetting the map F and forgetting all of the marked points after the first n. Now, the resulting marked curve may not be stable. There may be some rational components which are now unstable. And we contract those to a point. And in that way, it can be proved that we get an algebraic map of stacks in this way between these two moduli stacks. Okay? Now, on the domain of this morphism, we have the Chern classes psi I that I introduced today. Now, on the base, we have different psi classes, which I introduced last lecture, which are defined in almost the same way, except that now the definition of stability is different in the two cases. In the case of MGN bar, stability just refers to the stable curve, whereas in the case of the moduli stack of stable maps, stability refers not just to the curve, but to the whole map. Because of that, there's a difference between the pullback of the little psi I to the total space and the capital psi I. I'll just remark, sometimes you'll see reference to the following terminology. The little psi I are called by Giventhal ancestors, while the capital psi I he calls descendants. They were actually introduced by Witten, who is the one who originally called them descendants. So I guess Giventhal's terminology ancestors is a small joke about that terminology of Witten. Actually, for those of you who are interested, the descendants are, in a certain sense, the study of the equivariant cohomology of the loop space of X, but I'm not going to get to that point today. Okay, now we see the following. This formula is wrong. I'm sorry. So now I get to my first big misprint in today's lecture. So that should read 3g minus 3 plus n, not 2g minus 2 plus n. I apologize. So please, if you have a hard copy of the talk, please cross out the 3 and put 2. Cross out the 2 and put 3. The point is that if k, the sum of the k is greater than 3g minus 3 plus n, then we're above the dimension of mgn bar, and therefore the product of these classes is definitely 0. You can pull that relation back to the moduli stack of stable maps and then rewrite it in terms of the classes psi I, and in that way, in genus 0, you obtain Witten's topological recursion relations in genus 0, and in higher genus, you obtain topological recursion relations which are due to Eguchi and Shung. Okay? This might be a good spot to ask if anybody has any questions.
Ezra, I have a couple of questions. Can you hear me?
Yes, please.
Yeah. So,
yes, I can.
First question is, so suppose you define those Gromov-Witten invariants. So first of all, let's say we forget the psi classes. Just here, you are looking at those Gromov-Witten invariants where you pull back classes from the target space.
Yes.
The question is, if I'm being very naive, I would say they count genus G curves which intersect cycles Poincare equal to those cohomology classes. Now, we know,
correct.
Almost never
yes.
true in practice. So is this, and so my first question is, if G is greater than 0, is it ever never true, that naive interpretation, or that's never true? And second question is, are there some conditions on X where this naive interpretation is true? Let's say for genus 0.
Yeah, sure. So first of all, I think above genus 0, the only cases I can think of where it would be true is if both sides of the equation are 0 for some accidental reason. I never want to say it's never true in genus greater than 0, but I can't think of any case where it's true. Okay? That's the first, to answer the first question. Now, when is it true? It turns out that it's true in genus 0 if the target is a projective homogeneous space, a generalized flag variety. In other words, the quotient of a reductive group by a maximal torus. I'm sorry, I got that wrong, by a parabolic subgroup. So, for example, projective spaces, Grassmannians, and spaces like that. In that case, it was proved by, well, I don't know proved, but stated by Kontsevich and Manin that that is the case. Okay. Even now, I'm not sure. There are Del Pezzo surfaces are somehow a bit like homogeneous spaces, except that they're not quite, and they have these positive anti-canonical divisors. Is it true in genus 0 for Del Pezzo surfaces? Does anybody in the audience know that answer? I actually don't know the answer to that question.
So I think for Del Pezzo surface, actually, it's true. For genus 0, I think.
I see. Yes. So somehow that's something very special about 2 dimensions. Yeah, definitely only in genus 0. It's something somehow very special about 2 dimensions. I think, and beyond that, I just don't know what the story is. Also, in some sense, okay, good. So that was your first question.
My second question is this, maybe you can answer this later after the talk. Now, so you define this, including these psi classes, these Gromov-Witten invariants. Now, there's one more thing you could define. Instead of integrating on mg bar, you look at mg, look at the closure of mg inside mg bar and integrate on that object. I mean, usually the closure...
I'm sorry, I can't quite hear you. Could you repeat the last couple of sentences? Okay. Instead of...
Yeah. So instead of integrating on mg bar, you can integrate on this check, which is look at the closure of mg inside mg bar. Usually the closure of mg is not the same as mg bar. So
right.
So that new thing. So I mean, I guess you can relate one with the other. This is a very big question, but I would imagine naively that the second object, integrating on the closure should be a more natural thing of interest. I mean, somehow the first thing is more interesting. So, is there a reason for that? I mean, the second one looks more geometric.
I've got 2 things. If you want, I'm very scared to say very much about the geometric nature of your question because I'm not an algebraic geometer. So I would say if you can manage to invite Rahul Pandre to give you some lectures on this, I'm sure he can answer this part of the question with very much greater care than I could now. I can't answer it at all. I know that he has written something about this in certain cases. I suspect that in 3 dimensions, there's some special story. Okay? But beyond that, I'm scared to say very much. As for which is more natural, I would say that because ultimately we'd like a topological field theory, that's somehow why I consider taking the whole moduli stack to be more natural, because I want the structure which combines all of them together in a single object somehow, rather than which is a sort of homotopy algebra for a modular operad somehow. For me, all of the moduli stacks mg and bar combine to give something called a modular operad. And then somehow these fibrations over those are somehow some sort of homotopy algebra. But it doesn't quite answer your question. It's a bit vague. Okay, I think it's best to say I don't know, okay? Any more questions? Okay. Now, so we have these, as it were, the origin of the topological recursion relations. That's that these monomials in the little psi classes, the ancestors, vanishes. And so Eguchi and Chung inferred from that many recursion relations. Now, first we have the genus zero recursion relations, which are, I've just written them out, you probably can't absorb them. On the left-hand side, we have the third derivatives of F0, and on the right-hand side, we have a product of second derivatives of F0 and third derivatives of F0, except that there's some modifications in the indexing. Note that the total number of descendants on the right-hand side is reduced by 1. And if you carefully calculate the total dimensions of the virtual fundamental cycles, you'll see that this relation is in fact consistent with the dimensions of the virtual fundamental cycles. So when I say that Witten proved this, what I mean is that Witten conjectured this, and then after the moduli stack and virtual fundamental cycle were constructed, it was possible to prove it. So this result is effectively proved by Berenden-Manin and Berenden-Fantecchi. Now, we can capture a large part of the content of this relation by the statement that the second derivatives of F0 lie in the power series ring of the coordinates UA. They don't depend on the derivatives of U. So another way of saying it is all of these functions are functions on the large phase space. And more generally, if we take the nth derivatives of F0, that lies in the n minus second filtrand of the ring of differential polynomials. If we go back, you recall that I introduced this filtration on the ring where we only take derivatives up to k. And so here's where I'm using that definition. Now, using the topological recursion relations of Eguchi and Chung, I reformulated those in terms of the following statement, which is analogous to the previous one, that Fg lies in the 3g minus 2 filtrand of the ring of differential polynomials. It depends on the derivatives of u, but only up to 3g minus 2 derivatives. And more generally, if you take n further derivatives, then you move up n terms in the filtration. Notice that this last line includes the result of Witten. Okay. Now the string equation. So now we finally get to the beginnings of the Virasoro conjecture. Remember that in the absence of the projective manifold X last time, we had the fibrations of Knudsen and Mumford, where we forgot a marked point on a stable curve and stabilized the resulting pointed curve. In that way, we obtained flat morphisms between moduli stacks. Now, the same thing holds in the case of the Kontsevich moduli stacks. If we have a stable map with n plus 1 marked points and forget the last one, then in addition, we have to stabilize the domain C of the resulting map. And in that way, we actually obtain a flat morphism of Deligne-Mumford stacks. And actually, just as in the case of where X is a point, it turns out that the fiber of this flat morphism is naturally isomorphic to C, the domain of the stable map. So by studying this morphism, what we obtain is the string equation, which is very close in formulation to the case that we had last time. Notice that last time we didn't have the different cohomology classes labeled gamma A. This time, where we before had tau 0, we're going to pick out just specifically tau 0, 0, which is associated to the identity element of the cohomology ring. So this is somehow also at the same time a generalization of the string equation and a generalization in the case, actually the case where if G is 0 and n equals 2, I left out that part of the equation, we get a generalization of the fact that gamma 0 is the identity element of the ring. Now we can reformulate the string equation in terms of the generating functions fg, and they become these equations. Now, I know this is probably not a really good spot for a break, but could I take a 2 or 3 minute break at this point? Just to allow people to, don't go far, but is that okay? Hello?
Yeah, that's perfectly fine, Ezra.
Yeah. Okay, I'll just be a 2 or 3 minute break. I'll be back very soon. Okay, thanks. I just need a glass of water and stuff. Okay. It's really, I should say, we don't have air conditioning here in Canberra, and it's 30 degrees today. So it's old. I'm guessing you have air conditioning where you are. Although it's probably hotter here than in Bangalore. Okay, good. Okay, I'm back again. Okay, is everyone ready to go?
Yes.
Very good. So if you take a second derivative of the if you take repeated derivatives of the string equation, then what you see is that the derivatives of our coordinates UA, let me remind you, the coordinates UA are you see they're the second derivatives of the potential F0, the generating function of genus 0 Gromov-Witten invariants. So actually, these derivatives here are generating functions for genus 0 Gromov-Witten invariants with at least k plus 2 marked points, okay? And we see that essentially these derivatives are the coordinates on the large phase space, except that there's a shift which is called the dilaton shift. That's a word from physics, and to be honest, I have no idea really what it means, but anyway, that's what it's called. And you see that it only occurs in the special case where A is the direction corresponding to the identity element of the cohomology ring, and K is 1. And that's the dilaton direction. Now what we see then is if we take our ring of differential polynomials and form its spec, so that's some algebraic variety. It's a formal algebraic variety, and it's what's called a jet space. It's actually the jet space of the Frobenius manifold, which would be spec of just F0 of lambda. And what we see is that actually the large phase space is the completion of this jet space at a single point. It's called the dilaton point, and it's the point where the coordinates in the large phase space take the values take these values. So actually, all of the coordinates of the large phase space you should think of as being close to 0, except for the special coordinate T1a, which you should think of as being close to 1. Okay? So what we see then is that the large phase space, the study of the large phase space will be a lot like the Virasoro conjecture picture from last time. It's a more representation theoretic approach to the study of the Gromov-Witten invariants. Whereas the differential polynomials, this ring generated by U and its derivatives, that's closer to the integrable systems picture. And that's our Frobenius manifold picture. So what we're going to be trying to do is compare equations written in one framework or the other. And in that way, we'll learn a lot. Okay, so now I can reformulate in terms of the formal exponential of the total potential, the sum over all genera, call that Z. And that's, as I explained last time, very closely related to Saito's tau function. We can rewrite the string equation as a homogeneous linear equation for Z, where L-1 is this differential operator. It's a vector field plus a quadratic function. And I've written it in terms of these shifted coordinates on the large phase space. It turns out that they are the somehow correct coordinates to use on the large phase space. The original coordinates T that we used are not correct. This incidentally means that when you're studying the Virasoro conjecture, you have to be very careful not to use formal power series in terms of T, because they're not actually the correct ring. You have to use formal power series in T tilde. And while most of the papers in the literature are correct on this point, often the paragraphs of explanation in between the calculations are completely false. As I'll give as one example, Giventhal in his papers on Gromov-Witten invariants speaks of a Lagrangian cone. Now a cone is a scheme with an action of the multiplicative group, GM. And unfortunately, his cone is indeed this formal space with just one point, and the multiplicative group does not act on that cone. Its formal completion at the identity does, but at that point, in my view, one should be a bit more precise in one's language. But in any case, I just have to warn you that this substitution, where we're going to focus on the coordinates T tilde, this subtlety is really fundamental to the study of the Virasoro conjecture. Now, I'm going to introduce another equation from the Virasoro conjecture, which is Hori's equation. So remember last time we saw that the equation L0 was very closely associated with the dimension of MGN bar. And likewise, Hori's equation is very closely associated with the dimension of the virtual fundamental cycle. So Hori introduced his equation for CP1, and it was generalized then to CPN by Eguchi, Hori, and Shong, and it was generalized further to all projective manifolds, and in fact Kähler manifolds, by Sheldon-Katz. So I'm going to give you Sheldon-Katz's version. What we have is we're going to introduce a matrix which is cup product with the first term class, the anti-canonical class of our manifold X, okay? And then we introduce this rather complicated differential operator, which is a certain vector field, which we'll come back to, plus a quadratic potential, plus a constant. And that constant is this explicit Chern number on our manifold. Note that that number vanishes precisely if we have a Calabi-Yau threefold. If we have a Calabi-Yau threefold, the first term vanishes because R is 3, and the second term vanishes because C1 is 0. Of course, it's possible that it vanishes in other cases, but in particular, it certainly vanishes for Calabi-Yau threefolds. Also, the potential also vanishes for Calabi-Yau threefolds. And in fact, this equation of Horry is true for trivial reasons for Calabi-Yau threefolds. Now, the vector field L0, script L0, is given by this explicit formula. The first term perhaps looks a little bit like the string equation, except now we have additional coefficients, which are actually similar to the ones we saw in the equation yesterday, or 2 days ago, for the case of a pure point. So we get the number of descendants plus the dimension of the Dolbeau number P plus 1 minus R over 2. Notice that in the case of a compact symplectic manifold, you can construct an analog of this vector field except with PA replaced by half the Betti degree. But in that case, there's no Virasoro conjecture extending this. There's a second term in which perhaps looks a bit more like the string operator, except that now the matrix of multiplication by the anticanonical class enters. So that's our vector field. And actually, you can prove that L0 is a derivation of lambda u. It preserves, it's not just a differential operator on the formal ring of the large phase space, but actually of this very much smaller subring of differential polynomials. In fact, it even preserves the filtration. So all of that can be proved using Horry's equation and the topological recursion relations. So Horry's equation, he proved that L0 of Z is 0, and he also proved this integrability equation, which is necessary in order that the two equations, the string equation and Horry's equation, are consistent. I mean, what you can see is that otherwise this, if the right-hand side were not proportional to L minus 1, we would have a contradiction. Now let me rewrite Horry's equation in terms of the potentials Fg. Oops, there's a misprint here also. So if we apply the vector field L0 to Fg, then what we see is we get that quadratic polynomial in the case g equals 0. We get this explicit constant in the case g equals 1, and we get 0 for g greater than 0. I'll correct that in the final version of the lectures. Now, the proof of Horry's equation makes use of the dimension of the virtual fundamental class, and there are 3 further ingredients. So the first ingredient is the Dolbeau class, which is proved in exactly the same. It was proved in the case where X, the projective manifold, is absent. And now you see that we have the first descendant, k equals 1, of the identity element of the cohomology ring. But otherwise, the equation is really the same as it was in the case of a where X is a point. Now, the second equation, which is an ingredient of this formula, is the divisor equation. So actually, this holds for any divisor on X, or in fact, it holds for any topological cycle of degree 2. But since we're in the algebraic geometric world, we'll only need this for divisors. And we're only going to apply it to the Chern class of X. And so we have a matrix associated to any divisor, which is just given by intersection with D. And the divisor equation tells us how to insert the 0th descendant of a divisor cohomology class. There are 2 terms. One measures the intersection of D with the degree of the the map, and the other is a term which involves the action of this matrix cut product with the divisor, but in which the number of descendants is reduced by 1. And you can check that, again, this formula is compatible with the dimensions of the virtual fundamental cycles. And the last formula, which is needed in order to... I'm sorry, there's another misprint. Forget this last... I'll come back to this last formula. We don't need it yet in our equation. Okay? Now, using these two equations and the dimension for the dimension of the virtual fundamental cycle, you have to form a linear combination of these two equations, and then finally you obtain these equations. Okay? So forgive me for I've mentioned this last formula of Liebgobber and Wood prematurely. Okay. So now back to the Frobenius manifold with coordinates UA. I'm going to write a vector field on that manifold, which is given by this these explicit coefficients. The coefficients are actually linear functions on the Frobenius manifold. The linear terms involve the coordinates UA with coefficient, which is just given by 1 minus PA. So notice that in particular, they vanish on the subspace of divisors. And the other part is given by cut product with the anticanonical class. It is actually just the vector, the anticanonical class itself. So this is the Euler vector field. This is a very important vector field on the Frobenius manifold. And Hori's equation in genus 0 comes down to the statement that this complicated differential operator on the large phase space applied to the coordinates of our Frobenius manifold have the same effect as actually the Euler vector field on the coordinates. One nice way of saying this might be that there's a formal submersion from the large phase space to the Frobenius manifold. And we could say that that morphism is equivariant, where we place the vector field L0 on the large phase space, and we place the vector field minus E on the Frobenius manifold. So that's a sort of abstract geometric interpretation of Hori's equation. So now I'm just going to mention the statement of the Virasoro conjecture. I'm not going to give you any formulas today. So what we actually have is a sequence of additional differential operators on the large phase space whose commutators satisfy the same Virasoro commutation relations as we had last time. And these L-1 and L0 are the operators that I introduced for you. And the difficult part is to guess the formulas for L1, L2, and so on, such that they satisfy these commutation relations. Well, it turns out that it's quite straightforward to make sure that these commutation relations hold as long as m plus n does not equal 0. When n plus n equals 0, it's quite a bit more difficult to prove this commutation relation. So the difficult case is L1 commutator L minus 1 is 2 times L0. And to prove that, that's where we need this last formula of Liebgobber and Wood. The reason is that in the commutator, we get the left-hand side, which is a certain quadratic polynomial in the Dolbeau degrees of the cohomology classes. It's actually, as you see, a linear combination of the Euler characteristics of the sheaf of degree p differential forms on X. And using the Riemann-Roch-Hirzebruch theorem, Liebgobber and Wood were able to show that that left-hand side is actually a Chern polynomial. And it's given by this explicit formula. It's a 12th of R times the Euler class plus twice this other formula involving the first Chern class and the penultimate Chern class. So this is, it's a very easy formula to prove using the Riemann-Roch-Hirzebruch theorem, but not particularly, I have no idea how to prove it in any other way. And actually the theorem of Liebig-Ober and Wood was that this formula and a similar formula for the Euler characteristic are the only two polynomials in the Dolbeau numbers, which are given by Chern polynomials. So it's quite remarkable that this rather complicated formula is exactly the essential formula that's needed in order for the commutation relations of the Virasoro conjecture to hold. So the Virasoro conjecture states that Ln of z is 0 for n greater than 0. And we have some partial results about this. It's known to hold in genus 0 for all symplectic manifolds. And in higher genus, it's only been proved for certain classes of projective manifolds, such as homogeneous spaces, del Pezzo varieties, and K3 surfaces. So it's a rather fragmentary subject. There's no particular reason to believe that it's false for general projective manifolds, but as far as I know, there's no particular idea of how it could be proved for some random, fourfold of general type. Very little is understood about how the Virasoro conjecture would hold in that case. Okay, I'll throw something out there. Perhaps non-commutative geometry will play a role in this. Perhaps by studying the derived category and relating the Virasoro conjecture to the derived category, it'll be possible then, and introducing non-commutative derived categories, a better understanding of this conjecture will be made. But I have absolutely no idea how to even begin to think about that problem. So the conjecture was actually stated for projective spaces originally by Eguchi, Hori, and Shung. Their way of conjecturing it was really quite remarkable. They had given a physics proof in the special case of the projective line. That was based on another conjecture of Eguchi, Hori, and Yang, in which they had conjectured that the Gromov-Witten invariants of the projective line were governed by the Toto hierarchy. And then from the Toto hierarchy, they gave explicitly a derivation of the Virasoro conjecture. So based on that, they then saw how to generalize that sequence of formulas to the case of projective spaces and indeed Grassmannians. And Sheldon Katz then found a generalization of that to all projective manifolds. And it's there that he needed the formula of Liebig-Ober and Wood. So this was proved for Grassmannians by Giventhal, and then Giventhal in collaboration with Bums and Kim. I think they proved it for more generalized flag varieties, and another proof has been given by Telemann. And I just want to close today by mentioning the Pandey. So remember, I mentioned the vector bubble over MGMR of rank G, whose fiber, at least over the smooth part, is just the algebraic one forms on the curve, and over the singular part, it's given by sections of the dualizing sheaf. Okay, so this vector bundle, using this vector bundle and its Chern classes, we are able to obtain generalizations of the Gromov-Witten invariants. And in particular, the Euler class of this bundle plays an important role in the subject. So that's lambda G, it's usually denoted. It was introduced by Mumford. And it's a class on MGN bar, which we can multiply monomials in the psi classes by lambda g. And you see that as long as k1 up to kn add up to 2g plus n minus 3, then we may get a non-zero rational number. Also notice that these numbers are just the usual Gromov-Witten invariants in the special case where g is 0. Because when g is 0, we're looking at the Euler class of the 0 vector bundle, which is 1. So another way of saying this is that these intersection numbers generalize the intersection numbers that we studied last time for genus 0. So it turns out that the Virasoro conjecture for, I forgot to say this, for the projective line in degree 0 is equivalent to the following formula, that these intersection numbers are given up to a non-zero coefficient, which is a Bernoulli number. They're given by the same formula as in genus 0. So that's a straightforward calculation using excess intersection theory. There's actually a similar formula in using the Virasoro conjecture for surfaces in degree 0, which gives a conjecture of Faber. So that was quite surprising, because that conjecture of Faber, nobody had really thought much about how to actually prove it explicitly, and then it just popped out from the Virasoro conjecture for CP2. So it's a very strange interaction between these different subjects. Actually, what happened was, with Pandare, I thought at least we should easily be able to prove the Virasoro conjecture in degree 0. Unfortunately, it turns out that it wasn't easy at all. It required study of formulas as complicated as this. This formula was later proved by Faber and Pandare, independent of the Virasoro conjecture. Okay, so I think that's a good place to end today's lecture. But I've left some time for questions if anybody has any.
So I guess if you can go back to the 9th slide, there was some formula that I was. Hello?
Yeah, hello, I'm here. Yep.
Yeah. So, yeah, a couple of slides before.
Oh, not 9. Which?
No, 9. So the one before, I think.
That's late. I'm sorry, your page numbers are different from mine. I've got 9 there.
Oh, no. So 9 meaning the number showing downstairs. At the very...
Yeah, I've got 7 here. I've got a contradiction between the numbering on your pages and mine.
No, I mean, what's being displayed on your screen, and there's a 10 in the blue line at the bottom, right? 10 out of 22.
Oh, 10?
Yeah, so, yeah, it's 9 there.
Okay, good, yeah. Oh? Sorry?
No, so now
I'm confused.
So maybe one more slide before.
Yeah?
Yeah, here. So I guess you...
Yeah?
So this one. Can you go back one more slide, perhaps? Yeah, so here basically you're, saying that, summing over these degree betas, you're getting these Gromov-Witten invariants as this formal series, which you are thinking of it as an element of this Novikov ring, right?
That's right.
But then you have defined these tau, k1, a1, and so on as, I guess, rational numbers. So,
yes.
Wouldn't this ideally be cohomology classes as coefficients followed by q to the beta, or?
No. I'm sorry. On the top line, yeah. I left out this, unfortunately. We only consider that definition in the special case that the cohomology class we're intersecting with the virtual fundamental cycle, that the dimensions are equal.
Oh, okay.
So I'm evaluating a cohomology class over a cycle of the same dimension, and that's a rational number. So it's not a cohomology class.
Okay, all right.
Does that help?
Yeah, because the usual quantum, cohomology product, these are like cohomology classes times q to the beta.
Yes.
Okay.
Oh, I see what you mean. That I could push those down now to mgn bar.
Okay. I see.
So there's a different approach, which is, good. So where did I have this there's this vibration, okay? Now, we have the virtual fundamental class on the moduli space on the left, right?
Right.
And we also have a fundamental class on the space on the right.
Right.
And actually, there's a more refined invariant, which is the relative virtual fundamental class. So that's the one you're asking about. Okay?
All right.
And so we could instead consider the monomial. Now we would have a diagram where we'd pull back the cohomology class on x to the n to the moduli stack on the left. We would multiply by the capital psi classes and now take the relative fundamental class and push forward. The relative virtual fundamental class and push forward to get a cohomology class on MGN bar. Okay?
Okay, yeah.
So that's what you're asking about. Or we could leave out the descendants completely. We could just push forward, pull back the evaluation and push it forward and get a cohomology class on MGN bar. And I can call that the ancestors. So that's in the original paper of Kontsevich and Manin. Okay? So somehow that's inappropriate for the talking about the Virasoro conjecture. So as you see, so first of all, for G equals 0 and n less than 3, we don't get any invariance that way. And we're going to need invariance in higher degree even when there are only 2 marked points or 1 marked point. So that's the first thing. And the way those are usually obtained from the invariance that you're talking about is to insert a divisor with 0 descendants and use the divisor equation and infer a sort of virtual formula for the 2-point invariant. But I'm just defining the 2-point invariant using an absolute integral. That's the first thing to say. The second thing to say is that those invariants of Kontsevich and Manin have much more information in them than the ones I'm giving you, because they implicitly can evaluate on any topological cycle on MGN bar, or certainly any algebraic cycle, but actually any topological cycle, whereas I'm only evaluating on tautological classes. So there's a lot more information in the topological recursion relations of Kontsevich and Manin than there is in the ones I'm discussing in these talks. And you've exposed me, you've pointed out that I'm throwing away a large part of the information. Now, let me make a bold statement about those more general Gromov-Witten invariants, nothing whatsoever beyond what I'm telling you. So they can be defined, but none of these conjectures involve them, and they're completely mysterious. Part of that, of course, is that we don't know very much about cycles on the moduli spaces MG and bar other than the tautological ones. I mean, we have a small amount of information, but it's pretty difficult to get more precise results. So, for example, the first non-algebraic classes are on M111 bar. These are associated with modular forms. And it would be quite amusing to write down some Gromov-Witten invariants which involved these non-algebraic cycles on M111 bar. But ultimately, it's sort of, to me, it's not very closely related to physical problems. So I'm a bit maybe less interested. But yeah, I mean, one can certainly start asking questions about that. So, okay, here's a challenge. Write down interesting Gromov-Witten invariants involving algebraic cycles on MG and R, which are not involving the first one of those is known to occur is in genus 2.
Could you repeat what you just said? Your voice.
Yes. Sorry. Yeah. So the only algebraic cycles in genus 1 on M1N bar are tautological. But in higher genus, in genus 2, it's known that there are algebraic cycles which are not tautological. So here's a challenge. I think it involves 20 marked points. So here's a challenge. How about no, maybe I've got this wrong. Maybe I should be saying that we're, oh no, I really can't remember. Or maybe it's in high genus with no mark points. I can't remember. Anyway, take an algebraic cycle in large genus, which is not tautological, and find Gromov-Witten invariant, which is non-zero for that cycle. Because those are the Gromov-Witten invariants that I'm not discussing in this. Okay?
One question. Hello?
Yes.
So,
yeah, I'm here.
Are the existence of those tautological cycles determined by the action of Sn, and looking at the representations that occur in the tautological ring, but that for MGN?
Sorry, what? I didn't understand the question.
So you said there are algebraic cycles on MGN which are not tautological, right? So the existence,
right.
Is it due to a Sn equivariant calculation, like determination of the Sn action, and then?
Well, the point is that I haven't mentioned the Jacobian.
Oh.
I mean, the answer is yes. I mean, I don't remember how many marked points there are. This is a paper of, who is it a paper of? Well, certainly Pandra is involved. I'm sorry, I didn't prepare for this question. But I think it's Faber. Is Graeber involved? I don't remember. Yeah. And the point is that it involves the Jacobian. And I haven't mentioned Jacobian of the stable curve C, of the curve C in any of these lectures. So you can get additional, if you like, Gromov-Witten invariants by considering the Arbor-Jacobi maps. And so that's a whole separate subject, which is extremely important. And I think maybe some of you know that that's very closely related to Pixton's relations. So you can't obtain Pixton's relations just using the Arbor-Jacobi map, but you can on the part of the moduli stack where you remove the, what are they called? So you keep only the curves of compact type. That is, those curves where the dual graph is a tree. So if you look at that part, so that the generalized Jacobian is compact, they're called curves of compact type. So that's an open subset of the moduli stack. And you can look at the part of the Pixton relations that just involves that part of the moduli stack. And those can be proved using Gromov-Witten invariants, just using Arbor-Jacobi map. But beyond that, there's not, not an expert. So I'm just talking more about the integrable system side of the story. I'm not talking about so much the algebraic geometry side of the story in these lectures, for which I apologize. Okay. However, feel free to send me questions by email also, and I'll be able to do a little, I'll be able to answer them maybe more accurately. Try again. Yep.
Last lecture, there was a discussion on so many different proofs of Witten's conjecture. There's by Kontsevich, Mirzakhani, Okunkov. So my question is this proof of, in special cases, there are proofs of Virasoro conjecture by Giventhal, etc. So which of these proofs of Witten conjecture, if any, is it a generalization of? Or is it something totally different?
It's actually quite different from what you're thinking. So there are two general stories. One is for curves. So I think it was proved by Alkukov and Pandre that the Virasoro conjecture holds for curves. And their proof uses the Virasoro conjecture for P1. And the Virasoro conjecture for P1, they proved directly from localization of the virtual fundamental cycle. So that's the same ingredients that Giventhal used in his proof. Giventhal uses localization formula for the virtual fundamental cycle. The point is that so what is the point? There's a action of the, sorry, I didn't prepare these lectures. So you have a torus acting on projective space, right? And so you can consider the action of that torus on the moduli stack of stable maps. And so Kontsevich advocated studying the virtual fundamental cycle by localizing it to the fixed points of that action. It turns out that the fixed points of that action, it has many components and each of them is smooth. So we can just use standard excess intersection theory. Well, it turns out that that program is extraordinarily difficult. And Giventhal was able to, by some clever shortcuts, he was able to implement that program to prove the Virasoro conjecture for projective spaces. But, and here's the caveat, his proof depends on the Virasoro conjecture for a point. So essentially, you've got two separate types of proof now of the Virasoro conjecture. One is the special case of curves, which ultimately comes down to the Virasoro conjecture for P1, which comes down to the Toda conjecture. So Okounkov and Pandurapande completely calculated the Gromov-Witten invariants of P1 and proved the Toda conjecture, and then they were able to prove the Virasoro conjecture from that. On the other hand, I think actually you can look in a paper of mine to see, in an analogy to last time, how the Toda conjecture actually implies the Virasoro conjecture for P1. On the other hand, they proved both conjectures simultaneously. So they don't use Kontsevich and Mirzakhani and other proofs of the Witten conjecture. But all the other proofs of the Virasoro conjecture rely on the special case of Witten's original conjecture, KDV. Okay? So I would say that's actually Giventhal's most important insight, that you could reduce the Virasoro conjecture for projective spaces to the Virasoro conjecture for a finite set of points, namely the fixed points of a torus action on the projective space. So I'll be able to talk a bit about that in my next lecture.
Okay, so if there are no other questions, let's thank Ezra.
Okay. And I'll see you tomorrow. Okay.